Okay, that's because we drew this squiggly little fellow with the blue, right? That fellow's derivatives could assume very high values, right? So if they assume very high negative values, then 1 minus y prime squared can be a negative number, and if that negative value is held for a very long interval, right? So suppose you hold the negative slope for a long interval and then you suddenly pop up back to the positive thing, then the integration overall, the integrand becomes a negative number. So if you integrate a negative number over a long enough interval and you integrate the positive part over a short interval, the overall result might turn out to be negative. So the value that is spat out by this for a candidate which is only close to y is equal to 0 in the sense of the 0 norm can actually do better in terms of minimizing this functional, because this one only spits out 0, but that other candidate might spit out a negative number which is smaller than 0. So in fact, no matter what value this 0 spits out, which is 0, I might always be able to find another candidate which does better than this, and then you say, oh, this is the best, I will find another one, but as for a slightly longer interval it holds on to a negative slope and then suddenly becomes positive, and that will do even better. So that way, no matter whichever you claim as your candidate strong extremal, there is always ways of making it slightly better. So there is, in the sense of the Euclidean space, there is always a direction along which you can travel and keep doing better in terms of minimizing the function, in this case the function null, that is G. Okay. So that is why there is no strong extremal, which is when you consider the 0 norm. So let us agree that in order to draw analogies from the finite dimensional optimization problems that we have seen so far, here is what we are going to try and do next. Okay. So the J comes in place of the F. Yeah. So earlier we had Rn, sorry, let's erase this here, and we had F, we had the domain which was D. Now we have these function spaces which could be some C0 or C1, of course over the real field. Yeah. Now we have this J, and instead of this domain represented by the curly D, let us represent it by a curly A. Okay. Also, the idea of norm is understood from the context, whether it is the 0 norm or the 1 norm, depending on whether we are talking about the strong extremal or the weak extremal. Okay. So how is the optima going to be now defined? What do you think? Remember the epsilon ball definition that we had given earlier? So translate that to this language. Yeah. So now, what are the fellows sitting inside here? Of course, it's an unfortunate abuse of notation, because this F here and the objects sitting inside here are also now F's. You can call them Y as they do in the textbook, but well, you can also look at them as F, functions essentially. So your choice is now going to be functions. Here your choices were points in the Euclidean space, here your choices are functions, right? So what will you say is going to be the definition of a extremizing or a minimizing function which minimizes this function null? By the way, why is this called a function null? Because it acts on a function, a vector in the space of functions, and spits out a real number, a scalar. That is what the definition of a function null is. It takes a vector. So you know, you are familiar with these function nulls, right? So for example, if you take a constant vector and if you take inner products of this of arbitrary vectors with this particular given vector, then that is also a function null over the real vector space, right? So it is basically something that spits out a scalar upon acting on a vector. So here the vectors are the functions themselves, so anything that acts on those functions and spits out scalars, they are function nulls. This need not be a linear function null, unlike that inner product example that I just gave. Okay. Alright, so what is going to be my definition of a minimizing candidate F? Yeah, let's look at this. J F star, okay, minus J F. What's this going to be? If F star is a minimizing candidate, what should this be? Less than or equal to 0 for all F such that, what is it? How do you translate this to the language you know? So this can be either 0 or can be 1 depending on whether you're looking at a strong or a weak extrema. Yeah. So there exists epsilon greater than 0 such that this is negative for all F in that epsilon neighborhood. So if you found a small enough epsilon ball, whether it is a 0 ball or 1 ball, at this point I am not saying that. Depending on that, I will call it a strong or a weak extremal candidate, okay. But at least you found some epsilon subject to a choice of a norm that you have already picked. So this is, maybe I am not sure if the color is visible from the back. So this is either the 0 norm or the 1 norm. It's a very unconventional notation I am using here. So be wary, okay. So this is going to be exactly consistent with what we understand, right. So based on the development of this optimization over finite dimensional vector spaces, here's what would probably make sense to look at. The following: you have J evaluated at F star. From there you transition to J evaluated at F star plus, so I am omitting the argument of F, you know it's X already over the interval A to B, alpha G. That's a specific kind of a perturbation, right? Very similar to this X plus alpha V, X star plus alpha V if you remember, and we call that, here we are already using G here, so we cannot call it G anymore. Let's call this psi of alpha. Do you see the analogy? It's very strikingly similar to what we did in the finite dimensional case. In your mind you have to just make the transition. This takes the place of little g because little g is now also a function here. But this is along a specific direction, along the direction of g to be precise. And there are so many different directions now. Yeah. So there are things like directional derivatives that now you have to be aware of. In what follows, maybe not today, but in the next module or the next lecture we shall see, there's something called a Gauss derivative which will pop up as a result of this approach that we are now applying here. Yeah. So we'll shortly see that. The Gauss derivative. That will hold the key towards what is a necessary condition for an extremizing candidate F star, okay. But all that in good time. The point is this: if you now think back on the proof mechanism in finite dimensions, here's what we had done. Forget about those constraints and all those manifolds that came in later, right, which said that you cannot choose a perturbation like this, right. We said that now you have to choose this parameterized in terms of alpha. Forget about that. Just think about the case where you could go in any possible arbitrary direction. Even there was a little crucial detail. What was the crucial detail? The crucial detail was this, that you find out all possible directions, take these to be unit norm functions, so that the magnitude of perturbation is characterized exactly by alpha, and find out that over a unit ball, which is the direction along which it gives you the smallest possible alpha, choose that as your epsilon. What guaranteed the existence of such a minimum choice of alpha? The Weierstrass's extremal value theorem, which was applicable to a compact set. And a compact set in Euclidean vector spaces was one that was closed and bounded, right. Unfortunately, in the space of functions, a closed and bounded set, yeah, need not be a compact set. So, we will end this discourse today with an example of that, so that it will leave you a little uncomfortable. The idea is to get you out of your comfort zone and make you feel uncomfortable about it, right. So, that the ideas that carry forward in Euclidean spaces very easily, the fact that they do not trivially follow in these function spaces should be impressed upon you. Let us take C0 to be our vector space, and let us define A in the following manner. Is this a bounded set? Of course, I have forced this. It is a bounded set, okay. Bounded set of continuous functions. What is going to follow here is that this is also a closed set, but this is not going to be a compact set, because there will be functions which you cannot minimize over this. What sort of a candidate are we thinking here? Well, you think of functions like this. Think of a pulse like this, yeah. A pulse with a magnitude of -1 between 0 and 1. So, is there any function here that can get you to exactly approximate or exactly match this? No, right? Because this pulse is not continuous at these 2 points, right? What if this pulse were an extremizing candidate for a cost functional? Can you think of a cost functional for which this will be an extremizing candidate? Sorry? Integral f of x over the interval 0 to 1, okay, and then these conditions have to be invoked. So, it is a, say, suppose you are trying to find out a candidate over the set A for integral f of x dx. This is going to actually do the best job of minimizing the area. It gives you -1, doesn't it? Because you have to bound the norm also to 1, no? You cannot make it indefinitely negative. So, this is the most negative you can make. Unfortunately, if you find a function like this that very closely approximates this, your friend will come up immediately contradicting you and saying, I will do even better by approximating it like this. None of you are actually going to get closer to the truth than the other. You keep playing this game ad infinitum unless you are allowed to include this pulse itself in this set, which it isn't, because this is a subset of continuous functions and the pulse is not a continuous function. Unless you are allowed to include this pulse somehow, you cannot actually go ahead and find the best candidate here. And that has got everything to do with the fact that this set, despite being closed and bounded, does not allow for such a search for an optimum. So, the fact that this is bounded is quite obvious. We will see that this is also closed. How do you see that it is closed? You take any sequence of a convergent sequence of candidates from that set, and that limit point, the limiting function of that sequence of functions, yeah, must also be part of this set. Yeah. So suppose you have f1, f2 dot dot dot, fk plus 1 dot dot dot, this sequence. Suppose this converges. So each of these are continuous functions taking values 0 at a and b, bounded in their norm by 1, yeah, and they all converge to a candidate, say f. To prove that this is a closed set, we need to show that f is also going to be continuous. Of course, f satisfies the terminal constraints. Of course, f is bounded here. That's no doubt about that. The only doubt is if f is continuous. So what do? Let's take 2 points x1 and x2 inside the interval a to b and find out x1 minus f x2. We can actually write this as f x1 minus f k x1 plus f k x1 minus f k x2 plus f k x2 minus f x2. Why am I doing this seemingly funny rubbish? Any idea? What does continuity tell me? That if your independent variables are closer to each other than a certain delta, the dependent variable would also be within some epsilon ball, right? That's continuity, right? Small enough changes in x cannot take you very far away. If you want to bound the extent to which the dependent variable has changed, then the independent variables also are within some small enough bound of each other. So this is the epsilon delta argument. It's like a game of cards, as I always say, right? You throw me an epsilon, I'll always be able to play a delta. If that's the case, then I have proved that it's continuous and I have won the game. Yeah. So you give me some small enough epsilon, I should always be able to find a delta. Yes. So it's the same epsilon delta business. So why have I written it like this? Any idea? Does it ring a bell? Here's what I'm going to do. Because that's what we always do, no? We take the norm. If I've written the norms like this, and then if I separate out these things term by term like this, does that ring a bell now? I mean, not necessarily numbers, these could be functions, these could be vectors. The point is there's something called triangle inequality that norms must satisfy. Does that help in visualizing something from here? This is smaller than or equal to the norm of this plus the norm of this plus the norm of this. Yes, correct. So this is smaller than the norm of f x1 minus fk x1 plus the norm of fk x1 minus fk x2 plus the norm of fk x2 minus f x2. How is this helpful? You've chucked an epsilon at me and challenged me that the limit of this sequence, say some f, had better be continuous. So you give me some incredibly difficult epsilon criteria to meet. I'm going to cook up a delta based on what I know about these members in this sequence and the f, and prove to you that there exists a delta such that whenever x1 minus x2 is smaller than that, the norm of x1 minus x2 is smaller than that delta, the norm of fx1 minus fx2 will always be smaller than the epsilon that you've chucked at me. Yeah, and that way I'll prove that this is continuous and therefore this is a closed set. But we've already seen that this being closed is not good enough to minimize a certain objective function specifically. the area under the curve. Yeah. So essentially the idea is closed plus bounded is no longer good enough, unlike in Euclidean spaces. Let's get to the business of how to choose that delta here, and we'll be done. Since this is a convergent sequence, there exists some k such that beyond that k, or some L rather, some little L, such that for fellows beyond that L, Fk minus F will be smaller than epsilon by 3. Now you say, why epsilon by 3? Well, there are 3 terms. So instead of bounding this by epsilon, I'll bound this by epsilon by 3. So the choice of that L beyond which, so here's the deal, there exists L such that for all k greater than L, Fk minus F, this is smaller than or equal to epsilon by 3. From the convergence property of this sequence, yeah, from nothing else apart from the fact that it converges, you must get closer and closer. So therefore, beyond a certain number L, you pick out any candidate k, and the difference between f and the fk, the kth term in that sequence, and the limiting function in that sequence must be smaller than epsilon by 3. So this gets bounded by epsilon by 3, as does this. After all, it doesn't matter at which point you are evaluating, no, x1 or x2, at all points it's true. So this one also gets naturally bounded by epsilon by 3. What about this? What do we know about fk? It's continuous. If fk is continuous, I can always find some delta such that when x1 minus x2, the norm thereof, is smaller than that delta, fk of x1 minus fk of x2, the norm thereof, is also going to be smaller than epsilon by 3. And that is the delta that I am now going to invoke here. So that this is smaller than epsilon by 3 because of the property of the sequence, as is this, and this is going to be smaller than epsilon by 3 by dint of the continuity of fk. So the total sum is then smaller than or equal to epsilon, and the delta that I have chosen is the one that satisfies the delta property for fk, subject to the epsilon being modified as epsilon by 3. Is this clear? The whole continuity argument rests on my ability to find a delta. You give me an epsilon, I should be able to find a delta such that whenever the x's are closer to each other than delta, the fx's will be closer to each other at those points than epsilon. So you give me an epsilon, my job is to find a delta, and I am saying this is the exact delta you should find. First, find out the candidates in that sequence which are closer to f, the limit point, that is f, than epsilon by 3. Pick out any one such fk, and with that fk now, you go ahead and search for the suitable delta that keeps your fk closer to, between x1 and x2, the fk evaluated at x1 and fk evaluated at x2, their norm, their distance is smaller than epsilon by 3. Pick out that delta, invoke that delta here. These two terms will automatically be smaller than epsilon by 3. That particular clever choice of delta, if it may be called so, will keep this term bounded by epsilon by 3. Therefore, the sum is bounded by epsilon, and I have found an epsilon, or I have found a delta rather, such that whenever x1 and x2 are separated by something smaller than that delta, this f x1 minus fx2, the norm, has to be within epsilon. So this is a closed and bounded set, and despite this being a closed and bounded set, you do not have a minimizing candidate for integration y dx. Something as basic as the area over this set cannot be found. It doesn't exist. And the reason is, despite being closed and bounded, this is not compact. So just checking for closed and boundedness over function spaces isn't good enough. These are crazy, weird things, okay. So we had better be careful about how we deal with them, and we should not make quick conclusions when dealing with these spaces of functions. That's the caveat that I basically wanted to drive home here. Okay. So when we come back next, we shall try and develop tools along these directions, this directional derivative, and we shall try and arrive at some conditions. For the most part, while dealing with calculus of variations, we shall be dealing with finding out conditions for weak extrema and considering the one norm. Okay. So that's all for now. Thank you.